Hi families, Dr. Mommy here. It may seem a bit abrupt that I'm talking about Vesalius and Harvey, biologists, and also Francis Bacon, a philosopher, in this class. Um, as a matter of fact, Francis Bacon is not the first philosopher we've met in this class. The first philosopher we've met in this class is also the first biologist, Aristotle. And as a matter of fact, his philosophy had a profoundly positive impact on science, and so did Francis Bacon. Francis Bacon was the first person to explicate the scientific method as we know it today. First, we start with observation. We try to find correlations within all these observations. We hypothesize that some of these correlations have a causal relationship. We experiment to test whether or not these correlations have a causal relationship, and we conclude from our experiments whether or not they do. That has been huge for science in general. So I cannot thank either Aristotle or Francis Bacon enough. And what I'm about to show you is something I recorded over 2 years ago that further demonstrates how philosophy impacts science, both for the good and for the bad, and how it affects the human condition. So stay tuned. I think this is going to be really valuable.
What is the difference between a biotech company that doses metabolically challenged patients with a vomit-inducing placebo and a biotech company that heals hundreds and saves millions of dollars in the process? Believe it or not, the difference is philosophy. Now, if you equate philosophy with a bunch of overpaid professors blathering about nothing, as most modern philosophers do, you are right to regard my claim with skepticism. Science needs them like a hole in the head. So, what does science need? Perhaps in high school you were taught that the scientific method involves observation, hypothesis, experimentation, and conclusion. Incidentally, this was codified by philosopher Francis Bacon. But what does the scientific method actually look like? Let's start with the first step of the scientific method, observation. Does observation mean that you only look at things you think should be causally linked so that you can prove that they are? This approach is called rationalism, and it was founded by René Descartes. Do you regard causality as illusory and simply seek to observe everything? This approach is empiricism, and it was founded by David Hume. Or do you quantify as many phenomena that might be relevant to the effect you're interested in, looking for quantitative correlation? This is induction. It is what philosopher William Whewell surmised was how scientific giants like Newton and Kepler made their revolutionary discoveries. At this point, you may want to interrupt me and say, it's cute that philosophers came up with these terms, but no actual scientist would take at least two of these approaches. I wish I agreed with you. Instead, I'll offer you just one of the many anecdotes I've accumulated in the past 10 years of my career in biotech. Recently, I worked at a biotech company creating therapies for patients with metabolic disorders. These particular metabolic disorders involve nutrients that you can't avoid without starving altogether. However, some people can't digest these nutrients, so the nutrients accumulate to toxic levels in the body. This biotech company engineers therapeutics to extract nutrients from foods which are toxic to metabolically challenged patients. The question then becomes one of dosage. What amount of therapeutic maximizes the benefits and minimizes the side effects? What they tried initially was pretty reasonable. Some healthy volunteers got a small dose, others got a double dose, and some volunteers got a quadruple dose. The hope was that the therapeutic effect would change linearly with the cause.
What I mean is that if you have a single dose, you get a little bit of benefit. If you have a double dose, you get twice the benefit. And if you have a quadruple dose, you get 4 times the therapeutic benefit by that dose.
What happened instead of a linear response was a logarithmic one. Going from a single dose to a double dose almost quadrupled the therapeutic effect, but adding another double dose only had a marginal improvement over the first double dose. That's not weird. It's often the case that if you take a tiny amount of a drug, you're not going to feel even a little bit better. And if you take a lot of a drug, you'll reach a saturation point where no amount of additional drug is going to give you any additional improvement. However, the amount of active ingredient they thought they were adding was within the linear range. Given these unexpected results, did this company quantify the active ingredient to see if its concentration was in fact within the linear range? No. Rather, they kept looking only at metrics they thought should correlate with therapeutic activity and only for a linear rather than logarithmic relationship. What they found was that as therapeutic activity changed with time, all their observations remained the same. What I did was look at as many relevant metrics as I possibly could. I did indeed find a metric that was logarithmically correlated with therapeutic activity, not just in the lab, but also in mice, primates, and humans across 9 different experiments. Now that you have observations, what do you do with them? Formulating a hypothesis necessitates that you think there's an underlying cause. But you may believe that nothing has causes and that observations are approximations of true reality. This is philosophical skepticism, and it has had many advocates throughout history, though Bertrand Russell has been one of the more influential in the sciences. Perhaps you think causes are unimportant. As long as your observation correlates with the effect you want, it's predictive, it works. This is philosophical pragmatism, and one of its most infamous advocates is also the father of progressive education, John Dewey.
There is a third alternative, and that is that correlation may or may not indicate a causal relationship.
The most recent advances in causality are one of the many contributions of objectivism discovered by Ayn Rand. You may be saying to yourself, no scientist thinks causality is unreal or unimportant. In that case, you will be as surprised as I was to learn that it's actually fairly common. In the case of the company I mentioned, they took a couple of samples of their aged therapeutics, ground them up into fragments, and looked for clustering of those components in what is called principal component analysis. What they were looking for were components that were stability indicating, a common term in the biotech industry to describe something that trends with the decline in therapeutic activity over time. There are 2 potential problems with that. One is that a therapeutic is often more than the sum of its parts. You can't always tell from its components what's going to extend the shelf life any more than you can disassemble a book into cellulose and ink and get an idea of whether or not you'll like the story. The other potential problem is that correlation doesn't always equal causation. For example, up to the year 2000, global average temperature was highly correlated with a decline in sea piracy. Coincidence? Yes. Yes, it is. When I found a metric that was correlated with the logarithmic therapeutic activity, I realized that the way this metric is distinguished from other metrics was the addition of a nutrient amendment.
You can think of nutrient amendments as promoting the growth of some things at the expense of other things. So, for example, if you have a very mixed garden and you introduce a lot of sunlight and very little water, you're going to promote the growth of succulents like cacti. If, on the other hand, you have a lot of water and very little sunlight, you're going to promote the growth of stuff like fungi.
Indeed, when I diluted the therapeutic, I saw activity go down that logarithmic curve. But with the amendment, I could make almost any dilution show high activity. I hypothesized that therapeutic activity was causally related to this nutrient amendment. If you have a hypothesis, how do you test it? If you can, You will hold everything else the same and alter only one variable at a time to see if there's a commensurate change in therapeutic activity. This, again, is the method of induction. I learned that both philosophers William Whewell and John Herschel have a lot of advice to offer about validating a causal connection between correlations. If up to this point you haven't found correlating metrics, or if you think causality is unreal or unimportant, you might try to prove a metric to be causative because it should be, even if it isn't correlative. In the case of the company I mentioned, they didn't isolate variables. They didn't separate metric A from metric B, vary their doses, and see how each affected therapeutic activity. Instead, they took a combination of metric A, which I had shown does correlate with therapeutic activity, and metric B, which doesn't correlate with therapeutic activity. Unsurprisingly, with this combination of metric A and B, they saw a commensurate change in therapeutic activity with increasing dose. What was surprising was that they concluded from this experiment that therapeutic activity was caused by metric B. That's like saying, we have this patient with an iron deficiency, let's feed him a steak sandwich. He's feeling better. Obviously, it's because of the bread. The first thing I did was validate that metric A was causally linked to the therapeutic activity. It turns out that different lots of therapeutic have different proportions of metric A, so you can vary metric A while holding another variable, such as metric B, constant, and see a significant logarithmic correlation in therapeutic activity in mice, what Herschel pointed to as one way of finding vera causa, or true cause, of a phenomenon. You can almost eliminate metric A from the therapeutic with a quick rinse in stomach acid. Incidentally, this therapeutic is taken by mouth, while preserving metric B. When you do, you eliminate therapeutic activity by over 90%. These results, along with 10 other experiments, are what Whewell called consilience, supporting evidence that a causal relationship exists. Phenomenal laws describe what happened. Kepler's laws describing the relationship between a planet's distance from the sun and the time it takes to complete its orbit, or the logarithmic relationship between metric A and therapeutic activities, are instances of Whewell's phenomenal laws. But I wanted to go deeper, to understand why the relationship to therapeutic activity was logarithmic. This is what Whewell called causal laws. Kepler identified the relationship between orbital time and distance, the phenomenal law, and Newton identified the reason for this relationship is the force of gravity, the causal law. I wanted to understand metric A and its effect on therapeutic activity. I knew the way to identify metric A was the addition of a specific amendment. Indeed, with this amendment, I could enrich metric A at any dose, even those below the threshold seen in healthy human volunteers. I discovered that metric A correlated with therapeutic activity in the lab, in animals, and in healthy human volunteers. My next step was to isolate metric A's amendment and see how therapeutic activity was affected. I confirmed that below threshold doses of the therapeutic, which is a mixture of mostly metric B and a very little metric A, there was no activity. However, when only metric A was mixed with the nutrient we were trying to remove from our patients' diets, there was removal. Alternatively, if the therapeutic was amended, it was also actively removing the toxic nutrient. This may explain why certain patients didn't respond to the therapeutic. Their bodies weren't providing the amendment needed for the therapy to be active. I decided to go deeper and isolate variables further by breaking the amendment down into its three main ingredients. It turns out that component 2 is very similar to a part of the therapeutic that was washed away as part of the manufacturing process. It's actually very nutritious, but it was removed to try to make room for more metric B. It turns out that simply skipping the wash step makes the therapeutic as active as component 2 and almost as effective as pure metric A with amendment. Indeed, this probably explains the logarithmic relationship between the therapeutic and activity. A little of the wash remains in the therapeutic even after manufacturing, but only at higher doses is the remnant wash in high enough concentration to support metric A. Skipping the wash step not only would have saved the company thousands of dollars per manufactured lot, millions in the short run, it has proved to be more effective in primates and very likely more effective in people. It would mean the therapeutic is likely effective for more patients, fewer non-responders, and remove more toxic nutrient from all patients. What's the conclusion to be drawn here? It should be clear that philosophy is inescapable at every step of the scientific method. If you do science, you have no choice about the fact that abstractions are guiding your actions. But you do have a choice about whether or not you're conscious of those abstractions. If you aren't, you're probably operating on the wrong premises without even realizing it, and the consequences are real. Pediatric patients dosed with a therapeutic that's effective at making them throw up, but not effective at healing them in the long term. But the value of the right approach can be seen in just a couple of months by a single contributor, millions of manufacturing dollars saved, and hundreds of patients healed.